morning, everyone. Is the sound okay? Okay, yeah, perfect. Well, thank you for the invitation. So I'm Lilia Zaourar from CEA List in Paris, and today I'm going to present you how we manage to explore RISC V architectures using VPSim, a virtual prototyping tool with the best trade-off between simulation speed and accuracy. CEA is a well-known French applied research and technology organization. LIST is its institute dedicated to smart digital systems. Within CEA List, we are about 1,000 researchers and engineers involved in various R&D projects in software engineering, simulation, robotics, data intelligence, cybersecurity, and computer engineering, which is my field. I belong to Systems and IC division, where our main motto is how could we rethink, design, and build responsible computing solutions for energy efficiency, intensive and low power computing, from hardware and software architecture to distributed systems using industrial use cases. We are very involved in the RISC V ecosystem since we are a member of the RISC V Foundation, the Open Hardware Group, and Eclipse Foundation. Of course, to build all these systems, we need efficient and performance tools from EDA, like virtual prototyping, for example. Indeed, virtual prototype plays a vital role in the assessment of your hardware. It helps you verify your system early before your hardware is available, as you may know. It parallelizes design phases and then increases design productivity. It allows to identify performance issues before development starts and continuous integration. To do that, virtual environment should be fast and functional accurate, leverage existing architecture component library and allow the integration of new ones, provide System C interface for integration with EDA tools, support various APIs for debug and trace on third-party debug tools, work with scripting for runtime, and contain virtualization, file system accesses, peripherals, and networking from virtual I/Os. CEA developed its own environment called VPSim to serve these purposes. Our tool offers a good trade-off between simulation speed and accuracy. Indeed, VPSim helps you to model various complex SoC systems, electronic board, and integrated IPs. It helps for early software development, as I said, performance profiling and debug, and hardware validation. It allows multi-physics co-simulation thanks to full support of FMI standard and System C TLM. We provide an easy and fast user interface in Python with a large and flexible IP portfolio. And as I said, rapid simulation of full software stack, allowing software debug faster. Of course, there are many other tools in the literature. Here is a big picture, both in academic and industry. We can roughly divide them in 4 categories, depending on your purpose, from software development to architectural exploration. We have cycle-accurate model, instruction-accurate ones, dynamic binary translation, and native and trace-based one. VPSim is really in the middle, as I said, to provide the best compromise between simulation accuracy without sacrificing simulation speed. Here is the global architecture of the tool. As input, we have this yellow, it's supposed to be yellow, 2 boxes, a high-level Python script that allow you to describe your platform. For example, what are the number of the cores, what are the type of the cores, how are they interconnected, and so on. And we took a binary of the software that you would like to test on your virtual prototype. We have various IP models, ARM, RISC V, peripherals, network on chip, memory hierarchy, and so on. Thanks to VPSim Platform Builder, we build the system and provide various statistics as output on hardware counters, but also for debug, profiling, and analysis. Here is a small example of a study we performed recently for automotive use cases. So the objective was to build a virtual prototype to simulate security application on various hardware configuration. We have tested 3 different ones. The first one in the left is based on a quad-core ARM V8. The second one is a RISC V core. And the third one is a RISC V as an accelerator of the ARM. We get various feedbacks, for example, the number of instructions required by each processor to perform the application, and insights on hardware counters like data cache, L1, L2, and even L3, network and chip, and so on. Thus, we help designers to dimension correctly the system. VPSim has a long story development on our lab. Here is the key milestones. So we are very involved in European project, particularly European Processor Initiative. We start at the first stage by giving VPSim to software developers. Then we enrich our tool on network on chip models, memory hierarchy. We also provided a bridge for co-simulation to industrial tools like Synopsys Virtualizor, for example. And at the end of this first phase, we had provided a full co-design methodology that allow you to simulate the systems and also to work with other simulators like Gem5. We recently, as I presented, explored some automotive use cases based on RISC V. At the second stage of the European Processor project, we developed non-uniform memory accesses models. Of course, our development also follow architectural trends. Since we are moving from monolithic chips to 3D and chiplet, VPSim will be soon chiplet aware. And we would like also to investigate emerging technologies like photonics for interconnect. We have various collaboration with multiple entities from academy and industry. And I put here our main publications. If you want to have a look on one specific point, please don't hesitate. You will get also numbers and comparisons for the different use cases. Last but not least, it's my pleasure to announce that VPSim has just been released as open source. I would like to thank all the contributors to the team, to this tool, and I hope we will get soon new ones. If you have any question, please don't hesitate to visit us at CEA booth. We can discuss and maybe collaborate later on. Thank you all.
Thank you very much. I think we can take time for one question, if that's okay.
Yeah.
Anybody got a question?
How easy is it to extend the model with your own custom IPs?
So, if I get back here, it depends. So we can use the FMI as a bridge to connect with external models, but you will have a few feedbacks, let's say, from this model, and we can put our hand more on it and develop a system-sieve wrapper, and in that case, we can fine-tune the feedbacks that you can have from this IP. Does it? Okay.
Thank you so much for your talk.